Hello everybody. So this is going to be the very first video lecture in software engineering for the rest of the term. And so I'm going to spend a couple of minutes talking about what the video lectures are going to try to do prior to going forward. And then if you have any questions, comments, concerns about what I'm trying to explain, please send me an email and I'm happy to answer those questions. Keep in mind that my email response time is currently about a day, so I apologize if I can't get back to your questions sort of immediately. So in the first half of the class, and actually this is how we're going to start off. So the first half of the class, we really wanted to focus on the sort of academic or theoretical perspective of how software engineering is practiced. And so we spent a lot of time going through each of the major workflows, a lot of the different stages in the development process, and a whole bunch of different tasks that are associated with a lot of those workflows or stages. So in doing all of that, what we try to do is, where possible, sort of indicate all the practical considerations around practicing software engineering. And we particularly did that around systems analysis, where we talked about how we should really focus on multiple people at the client to kind of gain an understanding of business requirements, and also the sort of architectural case study that we went through as part of the course as well. So what we want to do now for this sort of last half of the class is really hammer home some of the more fine-grained practical considerations for actually getting a job as a software engineer and being successful in that job. So today what we're going to do is we're going to spend a little bit of time talking about probably the most common software engineering task ever, and how to effectively perform that task, and how to identify when you need to perform that task. Going forward, what we're going to do is we're going to talk a little bit about some general topics like open source software and where open source software kind of fits into software licensing, and how software licensing impacts software design and how projects themselves are managed. That's a thing that many of the groups or individuals in the groups have addressed with me privately, particularly for those who want to market their project after the course is done. But that's a thing that we're going to focus on in a little bit of detail, just to make sure that everybody is on the same page in terms of what you can and cannot use in terms of incorporating open source software in a project that you're intending to sell to other users. So after that, what we're going to do is really try to look at some individual case studies of where software engineering has gone very, very well, and also where software engineering has gone very, very poorly. And the idea is that we'll try to look at some very common pieces of software and some projects that I myself have done, and kind of try to map the workflows that we previously talked about to those projects, and kind of try to give you almost that I don't know, like on-the-job kind of feel for software engineering that doesn't necessarily come across when you try to boil everything down directly to a textbook. The last thing that I want to talk about in terms of housekeeping is I'm finalizing all of the grades for the tests, and I have not posted those grades, largely because we have the makeup exam tomorrow. So for everyone taking the makeup exam content, the assignment on Canvas will update from TBD to the actual test questions tomorrow around the beginning of the normally scheduled lecture. At any point in time after the questions are posted, all the way to the time that the test becomes unavailable, you'll be able to submit something. So keep in mind that the test itself is valid for 75 minutes after the normally scheduled beginning of class, which means that at approximately 6:30, the test will no longer be submittable, and at that point you'll need to make sure that you've already submitted something for that exam. Once those makeups have been done, and once I've been able to take a look at those, I'll do one more round of making sure that all the grades are consistent between the makeups and the people who took the in-class exam, and then I will post those final grades hopefully toward the end of the week, but it may be over the weekend before I can get everything finalized. So be on the lookout for the test grades becoming available fairly quickly. So as we were talking about before, what we're going to do is we're going to really focus this time on a very common software engineering task called impact analysis that in a lot of ways can either make or break your career as a software engineer. If you're very, very bad at impact analysis, it's extremely unlikely that you will maintain a job in software engineering, and it is even more unlikely that you'll be able to kind of work your way up through the ranks of a software engineering firm. So it's all predicated on the idea that every time an engineer, every time anyone really makes a change to code, there is some impact to the system at large. So even if you go in and you delete a semicolon at the end of a bullet of a statement, for example, you can make the code no longer compile, and now because of a very, very simple change, a fairly catastrophic thing has happened. So ideally, what you want is that impact to be obviously a positive impact. So you want the system to become better because of the change, but you also want it to be fairly small, right? You don't want to necessarily be making these massive changes to the system because the larger the change is, the more it impacts the testing workflow. So for example, if you go through and you re-implement a feature from the very basic principles, what that means is that somebody is going to have to go through a very large amount of testing effort to make sure that the re-implementation of that feature retains all the same functionality as the previous implementation, but also fixes whatever bug or whatever consideration you were working toward when you actually made the original change. The worst case scenario is that, okay, maybe the software gets a little bit better, and after you check in your change, you notice that the bug is no longer present, but you've made a change that ultimately undoes something somewhere else in the system. So you've introduced some widespread issue simply because you wanted to make a change to fix a bug. So this is a very, very, very common occurrence. It actually is more common the more technical debt the system has. And so this is the first kind of practical consideration around amassing a very large amount of technical debt. If the technical debt of a project is sufficient, you can actually make a change in one module or one part of the system and break a completely unrelated part of the system because they might be related through a framework component that may not even need to exist. So this is often viewed as a sort of one step forward, two steps back situation, but based on the amount of technical debt, you could actually have a one step forward, 19 steps back situation where you're effectively playing whack-a-mole to try to fix bugs, and the entire time you're trying to do that, more and more and more and more bugs keep cropping up. That's kind of the worst case scenario for any software project. So all of the negative impacts that result in either a new bug or an old bug being reintroduced into the system, these things are typically called regression impact. And there's a special type of testing called regression testing, which we very briefly talked about in the testing lecture. And that special type of testing is really to go through the entirety of the system, and any change that you made to the system, you want to completely test all of the features that were affected by those changes. So what you want to do is you want to go through and make sure that every module or every subsystem or every large code block, whatever granularity you want, that was impacted by any change at all is completely tested. The problem with this is that, as we talked about in the testing lecture, that can become unwieldy. And so based on the number of changes that you've made for a particular update or for a new release, you could end up trying to test the entirety of the system, which could lead to problems. So these regression bugs or these regression impacts, tend to be some of the worst bugs from a client-facing perspective. And the reason is because these are bugs that clients will know to look out for. These are things that they have previously reported. Because they've been previously reported, you know that the bug or the functionality that the bug is in is important to at least one client. And the fact that it has been fixed before and now is unexplainably broken again leads many clients to lose faith in the entire development process of the firm. So while if you have a bug that is kind of a new bug, clients tend to understand and they're fairly amenable to that, particularly if you can get them a fix on a fairly reasonable timeline. If you have regression bugs that keep coming up, so every other update you're somehow reintroducing the same fairly large bug, that's when, even in sticky markets where software is very hard to get away from, you can end up having impacts to client adoption. So clients will effectively just stop using the application, recognizing that while things might be good for release version 2, it's very likely that release version 3 will add new functionality that they may or may not care about, but could break functionality from release version 2. So regression impacts, more so than most other types of bugs, can become extremely problematic from a marketing perspective because they drive clients to disbelieve the software firm in general, particularly around things about development. So even to the point where it can get to where you're proposing a new feature, or you're saying that in version 5 or 6 you're going to have this great shiny new piece of software, whereas sometimes without regression impact, people will kind of believe that and they will look forward to that release. If you have a history of regression impact, the client will actually just hear that you have potentially new and exciting ways to break existing functionality coming at them, and it will become extremely unlikely to adopt new releases, which can impact the software firm's ability to actually sell the application to begin with. So these are kind of all of the soft things around the practical considerations of regression that you kind of need to be aware of. Regression impact client relationships far more than a lot of other types of bugs. So as with most things in software, post hoc regression testing is never going to be enough. And so we talked about this in the testing lecture, that there's effectively no way to test every line of every method of every class inside of a project unless that project is fairly small. So if you're trying to exhaustively test your computer organization 2 class project, you could probably do that. In this class, maybe you can test every line of your course project. If you are working on something the size of Microsoft Word or the size of Slack or the size of Zoom, you're not going to necessarily be able to do that level of testing. And if you have very loose controls over regression impacts very early in the development phase, you can get to the point where you are forced to do exhaustive testing to make sure that regression impact doesn't affect clients after the release of a piece of software. So where impact analysis comes in is by trying to catch regression impact very early when you're actually making changes to fix bugs. So impact analysis is effectively the process by which you look at the piece of code that you're trying to change to fix a bug, and you look at all of the different software around that piece of code that you're changing, and you try to assess the risk of the change that you're proposing. So basically what you want to do is you want to make sure that the probable improvement in the software, so the reduction of that bug, the increase in performance, the whatever outcome you're trying to get, outweighs the risk of making the change and then introducing even larger issues into the new release. So what we're going to do is we're going to go through a fairly quick, fairly simple, straightforward example of how impact analysis works, how you can do it as a software engineer, and then go through 2 kind of very easy ways around the problems that widespread impact or regression impacts can have, and we will identify which of these is a best practice, and sort of outline why it's a best practice. So what we have here is we have a C# method, and the point of this method is to take in an array of numbers and return a Boolean value that determines or that identifies if that list of numbers has an even integer in it or not. And so how we've done this is with a simple for loop. We go through each of the numbers inside of that array. We say if any of the numbers modulo 2 is 0, then we're going to return a true value. Otherwise, we're going to rip through all of the elements in the list. We're not going to find that condition, and we're going to return a false value. And so remember from the performance degradation or performance bugs lecture, this does not have the performance bug where we find a thing and then return later. We're immediately returning the fact that we found the very first even number. So the most common thing that can happen is a person will want a new feature or some extension of this method to do something slightly different. And so in this example, what we're going to do is look at a request to add a new parameter that starts our algorithm here at some number other than 0. So we effectively want a start index to be added to this that says check for evens in this list as long as it's after this starting index. So if it happens at the very beginning and my start index is 7 and all of the values in the array after 7 are odds, I would return a false even though the numbers array itself could have an even earlier in the array. So the first thing we want to do is we want to identify the fact that this method itself is public. So the keyword public here, much like Java, indicates that anything that has access to this class, so anything that can load the assembly that contains this class, has access to this method. What that means is that third-party libraries can be calling this thing. Many different classes inside of your own project could be calling this thing. The class itself could be calling this method who knows how many times. And so what that means is there's effectively an infinite amount of spread that can happen when breaking this method. So if we were to go through and we were to change the condition, so here, between this change, what I've done is I've introduced the not sign, and so now instead of checking for evens, I'm checking for odds. And because we don't necessarily know how many other classes or how many other methods are calling this method, we know that we've introduced a bug, but we don't necessarily know how bad that bug is. If there's only one method that's calling this thing, we messed up one method, that's not that big of a deal. If you are now giving the exactly wrong result to hundreds of methods, or if the third-party libraries are referencing this thing and now you are breaking completely different systems, that's obviously a much worse situation. And so even something as simple as changing a single character can have a very widespread effect. And we know in this case it's particularly widespread because of the public keyword. So that's a thing that we kind of have to keep in mind when we're looking or reviewing code that we want to propose a change to. If you change anything to do with the public method, you are exposing yourself to the largest amount of spread possible with your change. So if your change is incorrect, you could be breaking a lot of different things that you haven't necessarily even considered to do. So this is kind of an obvious situation, but you can also kind of extrapolate this in your mind to any number of different changes you might want to make to a method, and all of those changes might be much more subtle than this. And so going back to program comprehension as a thing that is very important for software engineering, if you are making effectively trial and error changes to a public method, that is probably the most risky thing that you could do in terms of impact analysis. And that is the type of thing that could get you on the short list for reduced work, so to speak, just because the changes that you make are fairly risky comparatively. This is the thing to keep in mind because you want to be cognizant of the impact that your change has on other people. And I'm sure that at this point in the course projects, you're fairly aware that those changes, those impacts can be fairly large. So that's a fairly simple change we wanted to make if we wanted to change the logic inside of the method. But even worse, what happens if we want to actually change the signature? So like I said, what we want to actually do is we want to introduce a new integer parameter and change this starting index from 0 to some new number. And so in order to do that, what I have to do is I have to introduce this new parameter called start. So the problem here is I may or may not have changed a method that other methods are calling inside of my project, and now areas of my project, specific modules, may not even compile anymore. That's actually a fairly good outcome, because at least then I would know to go and fix those methods, and after fixing those methods I would know that everything compiles and should be the same behavior as it was before. However, like we were just saying, the method could be called from a third party. And so if the third party is calling this method, you don't necessarily have access to that code, and that code doesn't necessarily have to be compiled by you in order to be used at runtime. So what you can do is you can introduce regression breaking changes into third-party systems, potentially dozens of them, and what will happen is it will pass all of your tests. It will go out into the wild, and as it is consumed in the wild by those third parties, all of the sort of integrations will fall over, and it's very unlikely that you'll be able to identify that at test time, because you may or may not even have access to those integrated systems as the software vendor. So this is a particularly problematic situation for software companies. You don't necessarily want to be adding things or changing or removing things from public interfaces after you have released the software into the wild, particularly if it's available to third parties for integration. So many modern languages have what are called optional parameters, and optional parameters will certainly fix this in some ways. And so what we could do, C# has this, C++ has this, Java has this idea. You can add a default value to that parameter. That default value will be read anytime a caller does not have a value for the parameter. And so in this case, we would get the exact same behavior. This right here should be a start, but you get the idea. You would have the same behavior as you would before, but the caller has the option of supplying a start value and changing that behavior to be the extended behavior for the new sort of feature. This is okay, but it's also widely considered to be a source of technical debt, and the reason is because you may have 3 or 4 or 5 or 6 different parameters that you need to add, and as you add optional parameters, you effectively are providing spaghetti code to another person to consume. So what you're saying is a lot of these values are optional. If you want to use the third and the fourth and the fifth one, but you don't necessarily want to use the first and the second one, it is entirely up to you to figure out what the default value should be for your use case. And the person who comes behind that developer that's consuming this method with a large number of optional parameters will then have to do a significant amount of work to understand what that original developer was doing in order to make the correct call to get the behavior that the caller expects. So while from a language feature perspective, this kind of fixes the issue, it doesn't necessarily fix the issue at scale. So this is the kind of thing that you could definitely get away with in a course project. You could certainly do it for the project in this class. And it's an easy way to make sure that you're not breaking someone else, but it isn't necessarily sustainable for a system of 50 million lines of code or a system that has to be maintained asynchronously by a very large group of people over a decade, for example. So the commonly sort of used best practice around the situation is often called an override hook. And what we have here is an example of one of those hooks. So what we've done is we took our initial algorithm, and here we see that start is put in the place where the 0 used to be. And we've taken all of that algorithmic behavior and we've put it into a new method with a signature that does not have an override value on start. The caller is required to provide a start, and that start is then fed into the algorithm and used as the initial place to look for an even value. But in addition, we have an override for that new method that matches the old method signature. And here, what we have is in that method signature, we have defaulted the value 0. And so we've done the job of finding the default parameter for the user. And now, even if you are a third-party user, if you're calling this method from a class that has never actually even seen the source code for this class, you have the option of either providing a numbers list or an array, or providing that array in addition to a start variable. And it is widely known, or sort of anecdotally known, that developers are less likely to misuse this situation where you have two choices to make than a method that has even a single optional or overridable parameter. So this is considered to be a better practice, largely because A, it's more maintainable, and B, the old code, or the code that has been calling the original version of this method for God knows how long, is completely unaware that this new method override even exists. And effectively, this new override for our new signature acts as a pass-through. So it is able to take that default value of 0 and pass it to the new method and implement the old algorithm using the new algorithm. And so we've sort of eliminated all of the risk associated with making the change to this method. So in general, this kind of example that we just walked through gives you an idea of how you can kind of approach making changes in a mindful kind of way. So the first thing you want to do is you want to identify the amount of downstream code you have. So if you are making a change to a framework method, if you're making a change to a framework class, that change is inherently riskier than if you're trying to make a change to a single application, or if you're making change to something like the UI, that is sort of the end of the trail. The second thing you want to do is identify the protection level of that code. And so like we said, public is certainly the riskiest. It could be accessed by third-party vendors. It could be accessed by God knows how many different modules inside of even your own system. And then obviously the counter of that is something like a private variable or a private method inside of Java or C#. And so those changes tend to be the safest because the impact is localized to only that file or that class effectively. So you can more easily go through and actually take note of all of the impacts that your change could actually have. So another thing is if your change itself includes more than 3 methods, what you should definitely do is you should take a step back and you should understand if your change is large enough or if the bug itself is gnarly enough that it should actually require that level of change. These things can very quickly bloom into what are called tangled commits. And tangled commits are often the source of technical debt that people are completely unaware of until much, much later down the line. So maybe many releases after the fact, you'll become aware that because of tangled commits, you have allowed changes to source code that have not been properly tested. And because they haven't been properly tested, they've exposed the firm to excess risk. And also, you need to be aware that if you make the existing code aware of the change, then you have to regression test that old functionality. And so anytime you're trying to change the interface or the signature of a method, that should maybe raise a red flag in your mind that you should maybe have a discussion with the person who is over any of the modules that are accessing that code. And you should definitely bring that up in something like a Scrum meeting so that people can make you aware of any issues that might have cropped up the last time somebody made a change to the method, et cetera, et cetera. And the last thing is once you have fixed your bug, you need to go back and make sure that the original functionality works. So if you have added functionality, you need to make sure that not only the new functionality, but also the existing functionality works. If you have resolved a bug, you need to make sure that the features that did not necessarily have the bug, or the feature pathways through that feature that did not trigger the bug, also do not trigger new bugs now because of your work. Effectively, smoke testing in these cases is insufficient because you should always assume that no regression testing should be taking place on your code, because if regression testing was being done on your code, it would be very unlikely that you would have a bug to fix to begin with. So you always want to try to test things around the functionality that you fixed to make sure that you're not introducing new scary sort of regression impacts that other people would not be aware of. And so as a kind of sign off, I want to talk about Tangled commits. So I'm in a group chat that has been going on for maybe the last 4 or 5 years with a lot of friends that I have from college. And they will watch sports together, and they will comment on a football game, for example, over a group chat. And there's this running joke that when a person tries to catch a ball and then run much further than the person should run, and get way more yardage than the person ever needed to get on a particular play, they call that trying to be a hero. Tangled commits often present themselves as a software engineer trying to be a hero. Effectively, what you're trying to do is much, much, much more than the bug report or than the feature request actually asks you to do. So many firms have this idea written into their sort of mission statement that if you are trying to check in a bug fix, you should also leave the code better than you found it. In simple terms, that might mean something like reformatting the code if it's formatted really poorly. It could mean adding comments, but it could also mean doing things like refactoring code in order to make the code adhere to best practices, or in order to make the code more obvious what it's trying to do. But what you need to be sure of is that commits are logical, and each of your commits do a specific thing. So if you are trying to improve a piece of code and fix a bug, that should be 2 different commits. The first one should actually fix the bug, and then the second one should actually perform all of the refactoring tasks you need to do. The reason that this is important is, as we talked about previously, you want to be able to link metadata about what tasks you're doing to each of those commits. If down the line you recognize that a refactoring task ultimately introduced a whole bunch of regression impact, you want to be able to go back to that commit and remove that commit without necessarily removing the bug fix, which would allow you to remove the risk without removing the improvement that you made by fixing the bug. So as a general rule of thumb, what you want is you want a one-to-one relationship between the commits that you're actually using to fix problems or introduce new functionality to the bug report that you're trying to rectify or solve, or the refactoring task or the new feature implementation task that you're trying to perform. So anytime you get outside of this one-to-one relationship, that means either that you're taking multiple commits to fix the same bug, which typically means that the requirements are incorrect or your understanding of the requirements are incorrect, or you have multiple tasks or multiple bug reports in a single commit, which is a tangled commit, where you have a whole bunch of different stuff that's resolved by the same commit, and when you try to come back and reduce risk by eliminating the lowest sort of impact things in terms of new functionality or performance, you can't do so without actually reintroducing bugs. So in either of those cases, when you don't have a one-to-one relationship, you want to be mindful of why, and just be aware that that should not be the normal course of business. That should be kind of a special case. And with that, that's really all I have to say about impact analysis. On Thursday or on Wednesday night, there'll be another video posted specifically addressing software licensing and open source software. And so look out for that. You will also be shortly getting grades for the iteration 1 of the group project. And remember that iteration 2 of the group project is due on this Friday. As with everything for the remainder of the semester, we can be fairly flexible. If you need flexibility. So if you find yourself being unable to work for whatever reason, please send me an email and explain it, and we will do everything in our power to sort of help you out in any of those situations. So thank you for tuning in, and I will talk to you all on Thursday. Thanks a lot.